I am Matteo Farso, Director of the Gold Fairs of Italian Exhibition Group. It is a pleasure for me to welcome you at Vicenza Oro and T Gold. We're now halfway in these 5 days of the event, and I can draw a small balance of these first days, confirming that Vicenza Oro T Gold is a fundamental platform for the jewelry industry. We have had visitors from all over the world, and the strength of the Vicenza platform is that we managed to represent, together with T Gold, the whole value chain. We have 1,300 exhibitors, with a significant part being made by technology, represented in T Gold, an event which has become a leader worldwide thanks to the innovations presented by companies at every edition. And very soon, this will also find its own place in the headquarters of the Vicenza Fair, thanks to our building efforts that aim at reuniting in one single place the whole value chain. So the JTF is part of a program that goes hand in hand with the business, with events tackling topics which are fundamental for entrepreneurs to understand the priorities they have to work on to be competitive on a highly complex market and a highly international market as well. So we have started with the presence of 650 young students, tackling the important topic of the generational exchange. And today we will talk about technology, process innovation. So I would like to thank Legor, Massimo Poliero, Fabio Di Falco, Andrea Friese, and the whole team for working hard to enrich also this edition of JTF. And I wish you all profitable proceedings. Thank you. Good morning, everybody. This is our 20th edition, so we're not all that young any longer. Some years have gone by since 2004, when the first edition took place in Montegrotto. I don't know if you remember that. And this year, in September, we're going to have a new event, which is a Vicenza Symposium that Damiano will explain later on. So I'm here just to express my thanks, because apart from ENG, that has been supporting us for quite a long time, I have to say that this is the ideal venue with the T Gold event in the Vicenza Oro January edition. Well, JTF exists because we have speakers who year after year come and tell us something new, and I would like to thank them all for the good job that they've done also this year. I would like to thank all the people who work in the Legor team. The main reason we organize this event is that of gathering people who can work together for the growth of our industry, the industry of gold, silver, fashion. Fashion is becoming increasingly more interested in our industry. And we are here to bring to entrepreneurs, researchers, production experts, technologists together so that they can exchange their ideas and they can look at the future thinking about something different. Technology is evolving, companies must evolve, and it is very important to put together our knowledge and put it to the disposal of the whole industry. We all know that innovative skills are paramount. It is very important to be able to rethink one's own products and to reorganize processes. JTF is a help in this direction. and it can certainly be also a very useful way to see what's new. Please refer to our website, where you will find all what has been written about these topics at the Santa Fe Symposium in the United States, at the JTF. So we've got quite a lot of material which is available. What we need now is some young people, some talents, come into our industry to bring a breath of fresh air and to support our companies to tackle the future. I would like to thank Eddie Bell and Chris Corti, who have been supporting this project for a whole life. They've been together with us from the very beginning. I would like to thank Andrea Friso. I think Andrea Basso will join us presently, and they will chair our symposium, our forum. So thank you very much, and I would like to leave the floor to Damiano Zito of COReGOLD, who's going to introduce the new symposium that will take place from the 2nd to the 4th of September this year, with this new initiative that brings this international event back to Vicenza and our historical and cultural framework. We will even have the chance of being inside the Palladius Basilica during this 3-day event. Thank you. Good morning. Please raise your hand if you speak English. How many people speak Italian? Right.
So, Chris, please forgive me. Sì. Buongiorno.
So, good morning. I'm here for the presentation of the Vicenza Symposium. This was not in the agenda, but together with Massimo and Andrea, we decided that this was an important opportunity to be able to tell you what the Vicenza Symposium is. So, the Vicenza Symposium, why? In May 2022, the Santa Fe Symposium was concluded, and we thought that it was absolutely necessary to keep having a moment of sharing, a moment to get together, to put together all those that are passionate about innovation and technology. And personally, but I shared this feeling with Massimo, we also wanted to give back something that we have received. We have always participated in the Santa Fe Symposium, and we've always received so much. So we could not imagine a world in our industry without something similar. I mean, we did not receive the baton officially from the Santa Fe Symposium, but we have grabbed it, trying to start from where that conference ended to bring it to a more contemporary level, providing it with a more global connotation. I mean, when you inherit something, you have to try and make it even better compared to what it was in the past. Why Vicenza? Well, of course, we thought, where are we going to hold it? And then one day we thought, well, why not Vicenza? And here we have developed the most appealing part of the whole conference. The conference will take place from the 2nd to the 4th of September, 3 full days, and it will take place every second year. We will give the opportunity and the time to those who want to share their efforts to present them, and we will give innovation time to take place. We expect at least 100 paying participants. And I would like to add that we're trying to do anything to have the Basilica filled with participants, because we would rather have too many participants than too few. We will have 21 speakers with a very high quality level and significant contributions. 7 presentations each day, 45 minutes for each single speech. And now the most beautiful aspect. Personally, whenever I've attended a symposium, well, they used to take place in hotel ballrooms. Okay, the symposium also works in a ballroom, but think about being in the immense Basilica by Palladio. This is a fair playground for our ambition. The other extremely important aspect is that all the hotels we have selected are located close to the Basilica. They're right there in the center of Vicenza, so that for those 3 days, the Vicenza Fair is going to become a citadel of innovation. It is our target to make sure that all our networking activities, that is all what happens following the speakers' official sessions, are really the biggest added value of the conference. Another unique aspect is the quality of the conference. Apart from Legor and COReGOLD people who have made themselves available, myself, Valerio Doppio, Massimo, and Andrea Friso, we participate in the activities of the scientific committee, but we have decided to obtain the endorsement of the 3 most important luxury groups: LVMH, the head of industrialization at Bulgari, a representative of Richemont, the head of research at Richemont, and a representative of the Kering Group, that is the head of the technical department of Pomellato. Having them in our scientific committee provides us with a guarantee that our symposium truly has the ambition of being something that will last forever. We've also involved 2 FEM representatives, the German Institute for Research in Precious Metals, namely Ulrich Klotz, who's been an official skipper at the Santa Fe Symposium for 10 or 12 editions. He no longer works at FEM. He's a university professor right now. And Mr. Florian Bulling, who is now the head of FEM. Organizers, well, Massimo, myself, and Marco Carniello. This is how it started. I've explained the reasons to you from the very beginning. I mean, these 3 organizations believe that it is fundamental to take the inheritance of the Santa Fe Symposium so that Vicenza becomes a technological center in jewelry manufacturing. I personally believe that the number 1 reason to participate in the symposium is networking. Most likely, this is the only reason why people should attend a conference. It is important to listen to the 21 presentations, but interacting with the speakers is even more important. To speak with people, to develop ideas, to share ideas, to talk about the problems. Well, during those 3 days, this will be the most important target and will be the most important result for people attending the symposium. So we're looking forward to have a very high number of people. We want this to become a social networking event, and then it will be successful. To get to know the contents of the presentations, you just need to read the minutes of a conference. But as a matter of fact, a conference is networking and sharing. And the non-official moments, lunches, dinners, and aperitifs are certainly the best opportunities. Just a few data about the conference. We have many presentations about additive manufacturing, materials, techniques, from jetting to powder bed fusion. Combo works between additive manufacturing and CNC technology. AI in additive manufacturing, as well as applied to gem setting. Sustainability, traceability, trackability. We have 5 presentations from the fashion world. Cyanide-free galvanic solutions, fashion rules and laws, alloys, white gold without platinum elements, red gold alloys characterized by high hardness, amorphous alloys. I mean, we have a very wide-ranging portfolio of topics. But the most important thing is that we have received almost 40 papers, and we had to accept only some of them, and we had to discard some of them, unfortunately. About half of them had to be discarded. But we believe that this is a success because it increases the quality of contents, and you need to pick and choose. If we had had 20 answers, we would have had to accept them all. Participation has a cost of 1,260 euros. If you register before the end of February. This includes all lunches, all dinners. So the participant will only have to take care of travel and hotel costs. Of course, you can subscribe also in September, but the price will be slightly higher. We are supported by Meneghini Associati that will help us in promoting the symposium and in telling the reason why it is important to participate. This will be done both in person and through videos, so that the whole industry knows about the symposium and becomes aware of the advantages of the symposium, because it would really be a pity to undervalue this event. It is an opportunity to transform Vicenza into the world center of technology innovation in the jewelry industry. Thank you very much. This is our website. And just outside, we have representatives of Meneghini Associati that will promote the event and will also pay visits in the different halls, telling and explaining what the Vicenza Symposium is. They will come with guns and sticks to persuade everybody to participate. Thank you. Very well. Thank you very much, Matteo, Massimo, and Damiano, for your words. Let's now go to the core of JTF that is celebrating this year its 20th edition. We will start with the markets, as we have done in the past few years. This is not strictly connected with the technical and technological aspects, but it is a good way to put the technological world we're in into the right perspective. We will start with Dr. Daniela Corsini, who will talk about precious metals, monetary policies, and geopolitical risks. Daniela Corsini has graduated at the Bocconi University in Milan. She started her career in 2006 at Horizon Capital SA in Luxembourg, managing a localized portfolio on national unit trusts of emerging markets. In 2011, she started working with Intesa Sanpaolo within the research department, where she manages macroeconomic research for raw material markets, specializing in energy, agriculture, industry, and precious metals. Since 2011, she has been part of the CFA Institute, and her presentation today will guide us through the factors that predominantly affect the listing prices of precious metals. She will try to depict the scenario for 2025.
Buongiorno a tutti.
Good morning to you all. Thank you for a kind invitation to the organizers. Thank you to you all for being here. I have a very ambitious task ahead of me. President Trump is going to make forecasting even more difficult this year. Anyway, I'm going to share with you the forecast that we have drafted at Intesa Sanpaolo. Here you see the macroeconomic forecast for 2025 and 2026. In terms of world growth, we expect economy to be stable with a growth rate by some 3%. With extremely diversified dynamics depending on the local areas. In the US, we expected to see a growth by 2% to conclude the slowdown that we have witnessed over the last quarters. And the policies that have been anticipated by Trump should promote economic growth and inflation. In Europe, we should see a recovery with good growth rate, lesser than 1%, in line, pretty much in line with 2025. The main driver in Europe are going to be consumptions and investment with the next generation EU. The most important issues concerning the world scenario are all connected to the economic policies of the incoming American administration and the consequent geopolitical risks. We know what was proposed. We're going to see then over the year what is going to be implemented. But at this point in time, we know that the risks are for an increase in terms of growth, an increase in terms of inflation, thanks to all the measures that have been proposed, apart from the deregulation that has been anticipated and the investment in energy. But as far as I see it, the impact is going to be very limited, especially at the beginning, because you know full well there's energy investments are viscous. It takes time before you actually level up, and the deflationary impact of this component is going to be visible over the following years and not this year. All these policies make it much more complicated to perform as a central bank. Here I've represented the Fed, the American Central Bank, and the European Central Bank. Both will go on cutting interest rates for some months, but the risk is that the Federal Reserve in the US should stop cutting before anticipated. It might probably have the top of cuts at June last, and probably only once if inflation and economic recovery are going to proceed more rapidly than expected. We shan't forget again the role that expectations plays. Since we learned that Trump got elected, the expectations on the part of the markets have already started picking up, and the markets are already expecting growth, even though such growth hasn't materialized. This is why the Fed is playing a very important role. In Europe, risks are that of a slowdown of growth, so we expected to see growth less than anticipated, with the inflation being connected with the risk of a trade war with the US. Probably the European Central Bank is going to have greater cuts, 1% probably, in 4 different steps, and the implication in terms of interest of exchange rate as such that we expect the dollar to be strong. That is going to be next to parity, and it could be 1.0 to 1.03 against euro. Dollar is going to remain strong. Indeed, over the next 4 years, is going to be 1.07, with the risk of a dollar being stronger than expected, because given the economic and political backdrop, the US are probably the region which is going to be stronger and which is going to play the lion's share in terms of economic negotiations. As for the impact on raw materials, well, there's going to be extremely diverse, and it is pretty difficult at the moment to identify clear shifts. So you see that individual policies that have been proposed by the US administration may have different impact on different raw materials. Let me focus on the last bar, i.e. gold. As you see, that there are elements that are going to press gold upwards, and other policies that might bring about a decline in the value of gold. So in case of fiscal policies with lower taxes, that should lead to positive effects on the on dollar, and this will be the most important trend, limiting or leading to a decline in the value of dollar. As for China, we're going to see a lower available income in China, which is probably going to reduce question and the price of gold. And uncertainty should lead to an increase in the shelter goods demand. As for foreign policies, we expect that we might see a start of negotiations or perhaps a ceasefire in Ukraine over the next 12 months. This might cause lower geopolitical risk, so lower price for gold. But as a matter of fact, we believe that such pressure is going to be counterbalanced by higher pressure in the Middle East. Indeed, we think that the focus of Trump administration is going to be on the Middle East with all the difficulties that ensue. So altogether for gold, we expect that the stronger impact is going to be connected to the monetary policy, interest rates, and the strong dollar. And this should enable a stabilization in for the price of gold, slightly lower than what gold value is, and only afterwards shall we see a pickup in the value of gold. Now, let's have a look at what is happening with reference to gold. Here you see the comparison between the U.S. trend in orange and gold that has reached record results on Halloween in 2024. So you see that up until 2023, gold and US dollar was strongly correlated in a negative way, but this stopped when geopolitical risks increased in the Middle East. Indeed, you see that when Israel and Iran started their war that have very negative repercussions on the price of gold. On October 31st, we had the peak level of gold, a peak value of gold when the uncertainty was at its highest. And then on the bottom, you see interest rates trend. You see that over the past 3 years, we shifted from 0.3 to 5.5 interest rates. It is 4.5 now. It might get as low as 4%. But as you see, in terms of monetary policy, restrictive monetary policy, we are living very tough days. Central banks have played a very important role, especially so in emerging countries. In this bar chart, you see gold purchases by central banks. In 2022, as from 2022, we saw record years. The data for 2024 only consider the third quarter, but we expect to be very much in line with 2023. And it is quite shocking to see that in the first half of the year, 67% of purchases hadn't been declared. So we don't know exactly which central banks have actually bought gold. And looking at the preliminary data for the third quarter, apparently the bar is going to be even higher. Indeed, after 2022, we had an explosion of purchases because the sanctions against Russia worried emerging countries that they look at gold as if it were a golden opportunity to stock a very important resource which is not subject to sanctions and can be traded easily. On the right-hand side, you see the gold held and declared by the People's Banks of China. 50 million ounces have been bought over 22 years, and there has been quite an important increase over the past 18 months, and this led to this peak being reached in 2024. Here, the price of gold is seen without the inflation based on American salaries in blue and for Chinese salaries in orange. You see that after the depreciation of yuan in China, gold is very good investment. It is still advantageous to buy gold, and this will tell us that the purchase of gold and jewelry are going to be very strong in Asia, despite the risk connected to trade wars. We might see a temporary decline, but the long-term trend is still very good. I'd like to skip a few slides to look at the forecasts that I believe are more interesting for you. With reference to gold, I would expect a stabilization in a wide range at between 2,400, 2,700 is the range, with an average of $2,550. After the end of 2025, we expect to see the price of gold pick up until $3,000 per ounce, which might be reached in the following years. But, you know, with Trump administration, you never know what is happening. Now, as for silver, we expect greater volatility and stronger bullish pressure. 28 to 40 is the range of silver. The average price is going to be 31 per ounce, but there are greater risk for the value of the price of silver to grow. As for platinum group metals, we expect the price to picking up. The range are pretty wide. We expect them to be between 800 and 1,050. We are more positive for platinum than palladium, because there's a wider range of application, especially when it comes to use in energy. Thank you very much for your kind attention. I have completed my presentation. Thank you very much, Mrs. Corsini, and we now give the floor to Mrs. Giusti, who will talk about the challenges for gold jewelry. She got her master's degree in economics at the Catania University in Varese. She's an economist at the Industry Research Office of Intesa Sanpaolo. She is focused on the industrial policies research, especially so with connection to fashion and regionally on Tuscany and Umbria. She's going to look at the jewelry section in Italy with an important focus on international markets. She'll be sharing with us a quality assessment that have been involved in the business community. Mrs. Giusti has the floor. Thank you very much. Good morning for your kind invitation. With this analysis, we shall try and look at the gold jewelry industry. I think it would be very interesting to look at it in the wider frame of the fashion industry, which involves again, gold jewelry. In this here, I've represented a turnover trend, and shows us one main feature of this industry that may react even at most difficult times. This has been quite clear after the pandemics, and this is going to go on in 2023 and 2024. The fashion industry is slowing down as conditioned by weak demand We saw a slowdown in consumption in China. They play a very important role, especially so for the luxury high-end products. This has been an overlapping that obtained immediately after the pandemics, and this is due also to the price policies that had been adopted by the most important companies. In the second part of 2023 and in 2024 as well, we see that even in fashion, we see that turnovers are declining in the first 10 months of 2024. But for the gold jewelry industry, we see an ongoing growth of turnover, 5.7 over the past 10 months. Turnover is greatly impacted by the price effect. So, of course, if we consider rather than turnover, but we look at the manufacturing, which may enable us to understand the quantity being sold. In this chart, you see very well that there's a slowdown. It can actually be detected also insofar as gold jewelry are concerned. There is a widening gap between turnover and manufacturing capacity. Manufacturing quantities, and this again proves the previous data to be true also for gold jewelry. There has been a growth by 5.7 in terms of turnover, but the production has been reduced by over 7%, as confirmed also for the month of November. So what has led to this growth in terms of turnover? Well, competitiveness certainly on international markets. Indeed, this industry is always able to present and offer its products on foreign markets with a value growth by 44%. And comparing the gold industry with other elements of the fashion industry proves that this industry can always be different, but we're going to see in greater detail why this growth has been so remarkable. The industry, in fact, has confirmed its leadership in Europe. Italy is certainly the most important market for the production of jewels, and this is quite self-evident looking at this chart, with the leadership in terms of export, 9.8 billion of jewels exported. And this figure could be even an underestimate, because it would be better to look at the export in Ireland. We know that in Ireland no jewels are manufactured, but we could include Ireland, and even the export by France certainly are impacted by the connection with the luxury high-end companies that import products from Italy. Over 54% of the export from Europe are coming from Italy. Well, this growth has become apparent, leading also to an increase in terms of market share. So we grew more than our competitors, so much so that our market quota is equal to 11%. This makes Italy ranks 5th worldwide in terms of export of gold jewelry. Looking at the result of 2024, this requires some kind of interpretation. There's a growth by 44.5% that requires being better explained. We should look at the growth in terms of quantity, only 28.6% in terms of quantity. So this could be one first explanation of this important growth. And another important piece of information comes from the markets where we have exported. Exports towards Turkey have actually jumped ahead, and there are clear reasons for that. One is linked to the fact that with the geopolitical tensions strengthening, Turkey became an even greater hub in terms of logistics. And there is another effect connected to the import policies that are typical of the Turkish market that have made it mandatory for the business community to import jewels, especially semi-finished product. Again, this is the result of the specific policies adopted in Turkey. But if we do away with Turkey, if we don't consider Turkey, exports are pretty much in line with 2023. 2023, in fact, was already a very good year, both in terms of value and quantity. The role of Turkey is very strong. In this case, we don't have data in terms of quantity because we don't have such data as breaking down by province. But anyway, in this chart, you see that Turkey is importing jewels, especially from Arezzo, Vicenza, and Valenza. And as for Arezzo, well, Arezzo in 2024, in the first 3 quarters, exports have more than doubled as against the previous year because of Turkey in particular. And so if we don't consider Turkey, we have a growth in terms of export both in Arezzo and Vicenza, with Valencia remaining pretty much unchanged. And this tells us that these provinces can export in different markets. Indeed, we exported also towards the Emirates. This is a snapshot of what statistics is telling us. Unfortunately, there is some delay in us reading these figures, and this can be the basis for potential developments in the near future. To forecast what is going to happen in the future, and we're now celebrating the 8th edition. So we asked the business community together with the Club degli Orafi about their expectations, about their feeling, their sentiment in terms of turnover, whether they expected them turnover to grow or not. Well, the business community is pretty much confirming what statistics are already anticipating. Indeed, respondents are expecting growing turnover shift from 36% in 2024 to 2025 to 25. So actually they decreased. Respondents expecting a growing turnover is equal to 47%. International markets are playing a very important role, are going to play a very important role also in 2025. And in investments mirror the cautious attitude. We saw a decrease from 46 to 21 in terms of investments. This could be linked to the uncertainty, to the legislation, the potential delays in implementing the transition Plan 5.0, and this might lead to adopting a sitting on the fence attitude in terms of investments. What are the difficulties that companies should overcome? Well, certainly the cost of the commodities, cost of raw material is number one, as well as the fear lest domestic demand slows down and international demand as well. 30% of the respondents indeed identify this as a main difficulty to tackle at this specific point in time. Companies are very much impacted also by the results in terms of US elections. We looked at this data in December, and Trump had just won the elections when we carried out this interview. So we interviewed the business community to see what their expectation was in case of an increase of tariffs. Companies proved to be quite dynamic in finding new customers in different markets should tariffs be imposed in the US. We'd like to see now the role that we play on the American market. And this chart on the left shows what we've done in the midterm on the American market, and Italy has suffered the competition from emerging countries, as is evident here. And in this chart, we also see that we repositioned ourselves on the American market. We shifted from, this is the Italian quota, on imports from Italy, we shifted from 7 to 14%. because we've been good in exporting high-end products. And we're doing better than France. As a matter of fact, even France that are impacted by our own exports to France, through France to the US. The American market over the years has changed. If we look specifically, there are specific areas, specific states that are responsible for most of the imports. There are especially 4 states that import modules. These basically cover 79% of the export. New York exporting 46, then Texas, California, and Florida with different percentage. Apart from Texas, and Texas can be explained because of one of the most important large retailer, again in Texas. But looking at this map, we may very well understand what type of products are being exported in the US. Indeed, these states are the ones with greatest purchasing power, and they buy high-end products. Different areas show different capabilities in exporting. You see that Arezzo Vicenza export most of the gold jewelry, but on the right-hand side you see that American market has different ranges of importance. Torino exports half of its products to America. So the US play a very important role for Turin in particular. As of late, we recorded a declining trend in 2024 because of the uncertainties in terms of American purchases connected to the elections. Exports declined by some 9%. This is the figure for September, and it doesn't keep track of the last quarter, but according to the business community, the last quarter proved to be better. First because, again, the elections had been concluded, and because, of course, with Christmas and the end of the year, there are much more purchases being made. This market is certainly going to tackle very important challenges to react to the tensions, but we see that over the years this industry has got to an important position and may combine craftsmanship, which is typical of Italian productions, with the innovation capability, and this is going to be ever more important to be competitive in the future. Thank you.
Ringrazio la dottoressa Giusti.
Thank you very much, Mrs. Giusti. And now, I'd like to give the floor to a speaker who needs no introduction, Chris Corti. Chris Corti today is going to talk about the enhancement of the strength of high finest precious metals. He's a very expert technical speaker in the world of gold jewelry. He was always been one of the key speakers at the symposium. He's been always very active at JTF. He's going to be there at the Vicenza Symposium. He's also there as the Santa Fe Symposium. He's had more than 40 years of experience at the World Council, and before setting up his own firm in 2009, he got a PhD in metallurgy at the Sara University in the UK. And before devoting himself to the precious metals, he has worked in the energy industry in the UK and Switzerland. The subject matter of his presentation today includes a study on high finest precious metals that are weakened with a low strength, and the objective is that to improve their strength. In the 80s, an alloy was adopted, but it wasn't met with a great success. More recently, different alloys have been developed with the hardened gold alloy as pure as 99.5%. And some of them are now marketing together with microalloys with silver and platinum. His presentation is going to focus on the revision of existing literature. He had tackled the same subject in 2005 and include high pureness alloys. And now the floor over to Dr. Corti. Thank you.
Good morning. I'm going to talk in English. Right, improving the strength of high fineness precious metals. Pure gold, platinum and silver, like all pure metals, are relatively soft. Oh, better, thank you. Are relatively soft with low yield points and hardnesses, and this has several drawbacks in the fabrication of 24 karat gold, pure platinum and pure silver jewellery, limiting design possibilities, as well as making such jewellery heavier and prone to scratching and wear. This problem has traditionally been overcome by alloying to increase hardness and strength, and has led to the use of the carat golds, sterling silver, and 950 platinum, and the lower finenesses of platinum and silver in modern jewellery. However, for gold, especially 24 karat gold of purity greater than 99.0%, is the alloy of choice in the Far East, where it is known as chukam, meaning pure gold, and in the largest market, India, and its subcontinent, 22 karat gold jewellery dominates. These two markets account for around 40% of total jewellery fabrication, and the relative softness of both 22 and 24 karat gold is seen as a weakness. The development of stronger 22 and 24 karat golds has long been desired. For gold, the development of 990 gold, that's a 99% gold, 1% titanium alloy in the late 1980s, hallmarkable as 24 karat, overcame many of the deficiencies of 24 karat gold with good strength and hardness. But it has not met with much commercial success for several reasons. In recent years, however, there have been a number of hardened or improved strength 24 karat gold materials developed with finenesses of 99.5% or higher, some in commercial production, where improved hardness and strength have been achieved by micro-alloying, i.e. the addition of very small amounts, typically 0.3%, of certain metals, and these are attaining some limited penetration of the market. Microalloyed silver and platinum materials with increased strength and hardness have also been developed and are being commercialised. Until relatively recently, little information was published on such microalloyed precious metals, and that was mainly in patents, and there was little understanding of the metallurgical basis for such materials. The work on microalloyed gold was reviewed by myself at the 1999 Santa Fe Symposium and attempted to explain the theoretical basis for the microalloying of gold. Since then, further information has been published and interest in microalloyed silver and platinum has emerged. Furthermore, interest in hardening high fineness gold, carat golds, has been of interest. This topic was reviewed by the author at the Jewellery Technology Forum in 2005, but more research and information of relevance has since been published. Thus, some 10 years later, it is perhaps appropriate time to update progress and knowledge. This presentation initially focuses on the mechanisms of strengthening metals and then reviews recent developments by conventional alloying of pure precious metals, and then on microalloying of gold, and covers the following aspects. The microalloyed golds that have been developed in terms of their properties in comparison to those of conventional carat golds. The metallurgy, the theoretical basis for hardening and possible candidate alloying elements which could form the basis of microalloyed 24 karat golds. And published information on the compositions and practical aspects of jewellery manufacture in actual microalloyed 24 karat golds. Progress in hardening of 22 karat and other high karat golds, as well as platinum and silver, is also discussed. The advantages and disadvantages of such materials for jewellery application are considered. We look at the mechanisms of strengthening pure metals by alloying, as well as work hardening by deformation. There are essentially three basic mechanisms of strengthening or hardening pure metals through additions of alloying elements. Solid solubility hardening, dispersion hardening by second phases, and grain refinement. Solid solubility hardening. In hardening by solid solubility, alloying additions dissolve in the pure metal. That is, they are incorporated into the crystal lattice of the pure metal, and this results in the distortion of the crystal lattice, making dislocation slip more difficult. That means it requires more force to deform the metal. The degree of hardening depends on the relative difference in atom size of the pure metal and the alloying metal, as well as the amount that you add. Thus, in carat golds, it is well known that copper is more effective than silver in hardening gold, as its atom is about 13% smaller compared to silver, which is only slightly larger than the gold atom. In dispersion hardening by second phases, when a second phase is dispersed in the metal, it will cause some hardening. Alloys that form eutectics in their microstructure, such as the silver-copper alloys, are good examples here. However, if the second phase is present as very small particles dispersed within the grains or crystals of the parent phase, these impede the movement of dislocations during deformation and cause considerable hardening. Typically, in such alloys, the amount of alloying addition exceeds the limit of solid solubility, and second phases of different composition and or crystal lattice are formed. By careful processing, these can be precipitated out into the parent metal crystal lattice as dispersions of very fine particles. This is known as age hardening or precipitation hardening, and is commonly utilised in the carat golds and some platinum alloys. The 990 gold titanium alloy, which I referred to earlier, is hardened by a gold 4 titanium intermetallic phase, for example. It is also worth noting that dispersions of metal oxides, carbides, and other ceramic particles can also be used to strengthen metals. An example in precious metals for high temperature application are the oxide dispersion strengthened platinum alloys such as ZGS or ODS platinum, where zirconia or ceria or similar oxides are used. Microalloys, where very small alloying additions result in considerable hardening, also fall into this category of hardening by dispersed phases. Grain refinement, very small additions of certain alloying metals are often used to reduce the crystal or grain size of precious metals and their alloys. This can result in improved ductility, reduced orange peel surface on worked material, and improved strength. The hardening effect of grain size of a metal is described by the Hall-Petch equation, in which the yield stress is inversely proportional to the grain size squared. If we look at conventional alloying, here we're talking of adding alloying metals in amounts of at least 0.5% or more. The addition of 1% titanium to pure gold to produce 990 gold has been referred to previously. Other significant improvements to 24 and 22 karat golds have been described using conventional alloying approaches. Dutoit and co-workers at Mintec in South Africa showed that a 995 finest 24 karat gold containing 0.3% antimony and 0.2% cobalt can be age hardened to a hardness of 131-142 Vickers, depending on aging temperature, as shown in the table. And we can argue whether this is conventional or micro-alloying. My feeling is it's probably the latter. Fischer-Bühner, when he was at FEM, has demonstrated the use of circa 2% to 2.5% cobalt additions to effect significant strengthening of 22 karat gold with aged hardnesses of 200 to 260 Vickers, although this involved a relatively high solution annealing temperature of 900 degrees Celsius. And he also showed that a combination of cobalt and antimony, in total 1%, resulted in a hardness of circa 150 Vickers after aging, but using a lower solution temperature of 700 degrees. There is also a patent by Taylor, who patented a 0.4% cobalt containing 22 karat gold, silver, copper alloy, but with a small addition of boron included. And this attains a hardness of 134 after 60% cold work. It is not clear what improvement in properties has been achieved over normal 22 karat gold compositions. We now move to microalloying of gold. I'm going to repeat a lot of what I've said in my earlier review in 2005. But before I start, I just want to say something about the density effect when you're alloying. We must distinguish between the difference between the atom weight and the atom volume in an alloy. The higher atomic numbered metals are heavier and denser. Gold is a heavy metal with a density of 19.32, where silver has a density of only 10.5 and copper a density of only 8.93. Thus, in describing alloy compositions, we must differentiate compositions given in terms of weight percent and atomic percent. Weight percent, the relative weights of alloying metals present, and atomic percent, how many atoms there are of each metal in the alloy. This difference is illustrated with gold-copper alloys. An alloy of 50 atomic percent gold atoms and 50 atomic percent copper atoms, that is 1 gold atom to 1 copper atom, has a weight composition of about 75% gold, 25% copper. And that reflects the difference in the weight of the gold and copper atoms. We look at the theoretical basis for microalloying. In the development of improved strength 24 karat golds, we're looking at total alloying additions of 0.5% or less, typically 0.3%, and even down to only 0.1% in some instances. And this affects a dramatic strengthening of the gold crystal lattice. Such small additions are approaching those values typically used to control grain size by grain refiners, such as cobalt or iridium in karat golds. As gold is a low stacking fault metal, and stacking faults are a type of crystal lattice defect, control of grain size alone or in combination with cold work will not yield significant hardening in pure gold. So such small additions cannot work through grain size control only. Significant solid solution hardening by such small weight additions is only possible if the alloying metal is very light. That is, it has a low density and has a very small atom size compared to gold. If we examine the periodic table, the light metals that might possibly be microalloying additions are in order of density: lithium, potassium, sodium, calcium, magnesium and beryllium, as we can see in the table on the screen. If we assume a maximum alloying level of 0.5% and taking the lightest metal in the table, lithium, then a gold 0.5% lithium alloy, for example, is 12.55 atomic percent lithium, which is within the solid solubility range. This is 1 atom of lithium to every 7 atoms of gold. In comparison, a gold 12.55 atomic percent copper alloy is only 4.4% copper in weight terms, which would increase hardness in the annealed condition to about 40 Vickers and to about 80 in the cold work condition. So maybe a gold lithium alloy could provide some of the necessary property improvement by solid solution hardening. If we look at another light metal, calcium, a gold 0.5 weight percent calcium alloy is only 2.41 atomic percent calcium, which is quite small, only 1 atom in 40, and therefore would not be expected to provide much solid solution strengthening. However, reference to the phase diagram, which is lurking over there somewhere, I think, over here, on the right, reference to the phase diagram shows that there's virtually no solid solution of calcium in gold and that there is a eutectic comprising 2 phases, gold and an intermetallic compound, gold 5 calcium, which has a high gold content. If this phase is finally dispersed in the microstructure, then we have the basis of a possible alloy system that could provide improved properties through dispersion hardening. We find similar features to the gold calcium system in the phase diagrams for the gold potassium system, but less strongly, and in the gold beryllium, gold magnesium and gold sodium phase diagram, suggesting that they are less favourable for a microalloying approach. Another alloying approach would be to add rare earth metals such as cerium, lanthanum and dysprosium or gadolinium, as these also tend to have limited solid solubility in gold and to form eutectics and intermetallic compounds with gold. And we'll see a bit of that in a moment in the next slide. Some of the relevant features of their phase diagrams with gold will be shown in the next table. Some rare earths have been omitted from this table just for brevity. From this table, it can be seen that the light rare earths, there we are. From this table, it can be seen that the light rare earths are potentially suitable. The phase diagram for the gold cerium diagram was on the previous slide, down here on the left, and the similarity to the gold calcium system at the gold-rich end is evident. Also, as the heavy rare earths have solubility at the eutectic temperature in excess of 0.5%, but a very low solubility as the temperature falls, it is possible that they may be amenable to age-hardening treatment with the precipitation of fine particles of the intermetallic compounds on annealing quenched material at low temperatures. And if we just go back again, in the middle there we can see the gold erbium phase diagram, or the gold-rich end of that, showing that the limited solubility as the temperature falls, which suggests that it may be amenable. In the development of 990 gold, Gaffner describes work done by the Degussa company in Germany on other candidate alloy systems, which included the heavy rare earths. The basis for selection was the possibility of second phase precipitation, as the alloy containing a 1% alloying addition in solution was cooled from 800 to 400 degrees Celsius. From this table of probable hardening effectiveness was constructed, and I haven't put it on the slide, but it is in the written paper, which you can get when it's loaded up on the website. The fraction of hardening phase was taken as an indication of the hardening effectiveness. The reason for developing the 990 gold titanium alloy is obvious from this table, as it has the highest fraction. The promise of the rare earths and zirconium was also noted. However, in that work, a 1% alloying addition was being evaluated. If we consider only a 0.5% weight percent addition of rare earth, then from the solubility data at 400 degrees Celsius, we cannot expect much hardening phase to precipitate on annealing solutionized material at 400. Fortunately for us, Giusti carried out some tests on gold rare earth alloys at alloying levels of 1 weight percent and lower. Cast alloys were annealed at 800 for 1 hour. They were also cold rolled up to 95% deformation and subjected to age hardening treatments at a range of temperatures. The table on the slide shows the hardness values attained for gold alloys containing 0.5 of the alloying metal or less. From this work, it can be seen that the annealed hardness is little different from normal pure gold, although cold work material is much harder and in the range of improved 24-karat gold materials. Age hardening heat treatments are not very effective at these low concentrations, with the exception of the 0.5 weight percent gold yttrium alloy, confirming the view expressed earlier that in the consideration of the solubility data, the heavy rare earths suggested little age hardening was possible at these low alloying levels. Whether alloys of gold with the light rare earth metals show good properties was not known at that stage. It is difficult to comment on the results for the gold yttrium alloy, as there is no published gold yttrium phase diagram, but recent work by Ning indicates that it is similar to the heavy rare earths with some solubility of about 2% of yttrium in gold. So to summarise, the mechanism of hardening by microalloying would appear to be based on some form of dispersion or precipitation hardening by intermetallic phases of high gold content in alloy systems that form eutectics at high gold contents, and where the microalloying addition has little solid solubility in gold. So let's move on and just recap on improved strength 24-karat golds. As I reported in 2005, a number of improved strength 24-karat golds have been developed, some commercially available, and jewellery produced in these materials are in the marketplace, particularly in Japan. All have virtually the same melting point, colour and density as normal pure gold. These are listed on the table on the slide. It is evident from this table that while annealed hardness is usefully higher than for normal commercial pure gold, cold working results in significant hardness increases, and that some materials can be further hardened by low temperature aging heat treatments. Perhaps not surprisingly, the highest hardnesses are achieved in the lower purity golds of about 99.5 to 99.7 fineness. Most can be cast, but the best hardness values are achieved in the wrought condition, often coupled with aging heat treatments. From a practical standpoint, as far as published information tells us, these materials cannot simply be remelted and recycled without loss of strength, as the hardening microalloying additions lose their effect on remelting. As we shall see later, this is due to the oxidation of the microalloying metals on melting. The superior strength of these materials has a beneficial effect in manufacturing jewellery in that certain processes can be done that are difficult with normal 24-karat gold. For example, findings such as lobster claws and some difficult chain designs become feasible. It also allows lighter weight 24-karat gold jewellery to be made with obvious economic benefit. When compared to standard yellow carat golds, it can be seen that the improved strength microalloyed 24-karat golds approach the hardness of 22-karat gold in both annealed and cold work conditions, but are still some way behind those of 18-karat gold. So what are the compositions of these microalloyed golds? The patent literature indicates that the Mitsubishi Materials high-strength pure gold material comprises gold of at least 99.0% purity and 200 to 2,000 parts per million calcium and or beryllium, germanium or boron, whilst a further patent from Mitsubishi indicates just 500 to 2,000 parts per million calcium plus 1 to 50 parts per million of carbon. Calcium appears to be the main hardening addition. The 3O company patent indicates that the pure gold material contains 99.7% gold plus 50 or more parts per million of gadolinium and optionally 100 to 3,000 parts per million of calcium, aluminium or silicon. In a patent from Tanaka KK in Japan, an alloy for precision casting is claimed containing small amounts of hafnium and the rare earths. There's also other literature on gold bonding wires for electronics application that has relevance. In a paper, Lichtenberger and colleagues doped high purity gold of 5 nines purity with 3 to 30 parts per million of aluminium, calcium, copper, silver and or platinum. They showed that most dopants strengthened the wire during extrusion, and beryllium had the largest effect, but only calcium and beryllium had significant strengthening effects after annealing. This is explained on the basis of atom size difference in the gold lattice. Calcium ion atoms are about 30% larger, and beryllium atoms are about 30% smaller than the gold atom. There will be a tendency for calcium atoms to sit on grain boundaries and pin them. Various patents for improved strength gold bonding wires cite additions of bismuth, the rare earths, calcium with beryllium, europium and niobium, germanium, barium, yttrium and rare earths, or calcium and lead. The choice in this application, these appear to be popular choice in this application. These also appear to be the case for microalloyed golds for jewellery application. The exception in the range of alloys is the hard 24-karat gold alloy developed by Mintec. It was developed to overcome their problems associated with the other microalloy golds that use calcium and or the rare earths, i.e. the loss of strength on remelting due to loss, oxidation of the microalloying metals, and the expense and difficulties in making them. Hard 24-karat gold can be made and processed on conventional equipment and is amenable to remelting without significant loss of strength. The age-hardenable alloy is of 995 fineness and contains 0.2% cobalt and 0.3% antimony. It is based on precipitation hardening by a gold antimony intermetallic AuSb2 with the cobalt retarding recrystallization. The gold antimony phase diagram is a eutectic system at the gold rich end and shows similar features to those I showed earlier. We look at more recent literature on microalloyed 24-karat golds. Further research has been published since my review in 2005. The effect on properties of rare earth additions such as cerium and gadolinium to pure gold and gold alloys has been reported by Ning. He showed that small additions to both pure gold and gold alloys increase the strength significantly and retard recovery and recrystallization, as well as refining the grain size. The strengthening of gold is twofold. One, by solid solution strengthening, but Ning notes that the light alkali earth metals such as beryllium and calcium are more effective. And two, precipitation hardening by intermetallic compounds such as gold 6 rare earth, gold 5 rare earth, or gold 4 rare earth. Which one is formed depends on the atomic weight of the rare earth metal. The light rare earth metals are more effective than the heavier ones as they have lower solid solubility and form the higher gold content in intermetallic phases. In a study of a gold 0.13% germanium alloy, Lai characterised the cause of brittleness that he found. The gold germanium phase diagram is a eutectic system. he found that germanium tends to segregate to grain boundaries as a eutectic phase, which led to the brittleness. In a further study, he reported work on hardening of fine gold by 1% additions of beryllium, and he found that the beryllium addition increased the hardness of gold to about 2 to 1 Vickers, but that the alloy was brittle and fractured on attempts to roll it. The as-cast grain size was refined and the microstructure comprised gold dendrites and eutectic phase of gold and the gold-3 beryllium intermetallic. The phase diagram indicates there is almost no solid solubility of beryllium in gold. This work has relevance to microalloying since the use of smaller additions of beryllium are cited in many of the patents. The 2003 patent by Matsuda Sangyo claims the use of 0.12% yttrium and 0.02 to 0.18% calcium for hardening of 24-karat gold. Another patent by the University of Tokyo claims a gold X rare earth alloy, where X is selected from aluminium, gallium, indium, germanium, silicon and tin, and the rare earth is a rare earth element. An earlier 2004 patent by Tokariki Honton claims a harder 24-karat gold containing at least 99.5% gold and 5 to 1,000 parts per million of phosphorus, plus 10 to 1,000 parts per million of one of a group including antimony, copper, zinc, iron, cobalt, nickel, gold, silver and gallium. A Chinese patent claims a stronger 99.9% gold microalloy containing calcium and a rare earth element plus a grain refiner, while a 2000 patent by Ogasa claims an age-hardenable 24-karat 99.98% gold microalloy containing gadolinium that reaches a hardness of about 150 Vickers after aging. So I think in summary from all of that, we can say that the more recent literature confirms the use of calcium and rare earth additions as preferred microalloying metals, but other additions are also possible. It confirms age hardening as the major hardening mechanism, with the precipitation of high gold content intermetallic phases within the grains. And in the picture, it's a microstructure of the 3O company's pure gold, and we can see there are some precipitates on grain boundaries, but the whole of the internal grains has got a very fine distribution of the intermetallic hardening phase. I'm now going to move on and talk about improved strength 22-karat gold alloys. As noted in my presentation last year here at JTF on the benefit of titanium alloying additions to precious metals, 22-karat golds also tend to be soft due to the limited amount of alloying element that can be added, which is typically silver and copper. Fischer-Bühner developed 22-karat gold alloys containing cobalt or a mixture of cobalt and antimony, as I mentioned earlier, to harden 22-karat golds by conventional alloying. And these have increased hardness by age-hardening treatments, as discussed earlier. Similar work has been reported by Mintec in South Africa. In their 2000 paper, they reported on a new hard 22-karat gold alloy, but gave no details of its composition. It has a colour similar to conventional 22-karat gold, but can attain a peak hardness of 274 Vickers in the cold rolled and aged condition. However, in a later paper in 2003, they describe work on both 99.5% gold and 22-karat gold, that's a gold, copper, silver alloy, in which they study the effects of alloying metals cobalt, germanium, antimony, zirconium and vanadium in hardening them. There they report a maximum hardness of 274 Vickers after cold rolling and aging for a 91.7% gold, 3.84% silver, 1.96% copper and 2.5% cobalt alloy, which suggests that their hard 22-karat gold alloy is hardened by cobalt alone. They show a micrograph of cobalt precipitates growing on the grain boundaries and finer precipitates within the grains, but at that stage they hadn't identified what those finer precipitates were. Work at ProGold on hardenable 22-karat gold is described in a 2004 paper which initially examined the effect of cobalt and iridium grain refiner additions on 22-karat gold, silver, copper, zinc alloys. And it was made using a 95% copper, 5% cobalt master alloy. The highest hardness of 230 Vickers was obtained by aging a gold, 3.7% silver, 2% copper, 0.6% zinc, and 2% cobalt alloy, yet again demonstrating the effectiveness of cobalt additions. The effect of other alloying additions added via master alloys, such as nickel, gallium, and tin, gave gold alloys of good colour that could be easily attain hardness values of 160 to 170 Vickers, with an addition of nickel plus gallium being preferred. And here we can see some results that I'm just going to discuss in the next slide. And I showed this last year, so I'm going to move on quickly and just talk about them. So 22-karat gold alloys, I spoke about last year, demonstrated that titanium alloy additions act as a grain refiner and allow substantial age hardening. And we saw in that table some results. The commercial use of a 22-karat gold alloy strengthened by titanium, based on this work by the Titan company in India, has allowed jewellery products to be marketed that show a 30% weight reduction compared to conventional 22-karat gold alloys. The figure on the bottom left of the slide shows a hollow bangle in their new alloy. That on the right shows a solid bangle. And my understanding is it's about 0.5 weight percent titanium is the alloying addition. And let's just talk about some of the practical aspects of making jewellery in these microalloyed golds. In summary, these are that you can investment cast and fabricate by conventional technologies. You can make some products that are difficult with normal 24-karat gold, as I said earlier, some chain designs, springs, screws, catches, and other findings. You can make lightweight, strong chains with good wear properties. Melting generally needs to be done in an inert atmosphere to prevent oxidation of the microalloying metals. Therefore, they cannot be made easily in a small workshop situation by conventional melting in air. As with normal 24-karat gold, soldering must be consistent with local national laws, and in some countries, use of a lower 22-karat solders is allowed, although there may be limits on the amount of solder used. However, another factor is the temperature of soldering, which can lead to a loss of work and age hardening in the vicinity of the soldered joint. Laser welding may offer a better solution there. There are also very low melting point 22-karat gold solders, I might like to remind you, and one solder has a melting point of only 361 degrees Celsius. Polishing should be easier than conventional 24-karat golds, as they are harder. And Bernardin, in his paper at the Santa Fe Symposium, noted that castings require procedures similar to those for platinum. Recycling of scrap is generally not viable due to loss of strength on remelting, as we've discussed earlier. The Mintec alloy containing cobalt and antimony is an exception here. However, remelting should allow the gold content to be fully recovered after use. Right, let's just move on quickly to the microalloying of silver. In principle, it will be evident that the same approach for microalloyed gold could be applied to silver. The developer of pure gold also developed a material pure silver, which is a 99.3% silver microalloyed material, and this is being marketed in the USA. It is claimed to be easy to work, as it does not require annealing, is very tarnish resistant, casts well and is harder than sterling silver. The patent covers microalloyed gold, silver, palladium and platinum materials. In the case of silver, an alloy of at least 80% silver is claimed, containing the rare earth gadolinium in the range of 50 to 1,500 parts per million, with optional further additions of alkaline earth metals, silicon, aluminium and boron in the range of 50 to 15,000 parts per million in total, with hardness values of 130 Vickers or higher and a Young's modulus of not less than 7,000 kilograms per square millimetre. A further embodiment of the patent claims an alloy of at least 99.45% silver with 50 to 5,000 parts per million of gadolinium, plus further optional additions of the same metals. Hardness values of at least 120 Vickers and a Young's modulus of 7,000 kilograms per millimetre squared are claimed, with hardness rising to at least 140 with 50% cold work. These materials are claimed to be heat treatable. The use of gadolinium is claimed to be the most effective hardening element and results in a high Young's modulus. These small additions do not affect the colour. And lastly, let's talk about microalloying of platinum. Microalloying of platinum should be possible. Of course, oxide dispersion strengthened platinum, as I mentioned earlier, for industrial applications has been on the market for many years. In a patent from Japan, a hard, high-purity platinum alloy containing 10 to 100 parts per million of cerium is claimed that has a good hardness, luster and tarnish resistance, suitable for jewellery manufacture, and is at least 99% purity. Vacuum or inert gas is required during melting to prevent loss of cerium by oxidation. A platinum cerium phase diagram shows characteristics similar to that of the gold cerium system. For cerium contents of 0.03 to 0.3%, hardness values of 60 to 102 were obtained compared to 40 Vickers for pure platinum, and hardnesses of 120 to 136 for 950 fineness platinum alloys. A commercial alloy UHP platinum from Japan appears to be a microalloyed platinum at 999.5% fineness, but little information is available. The Agasa patent, that I mentioned earlier, also includes platinum materials, and this claims platinum alloys of at least 85% platinum containing gadolinium and the other optional elements listed above for silver, preferably calcium, in the range 50 to 15,000 parts per million in total. Cast hardness values of at least 120 Vickers and Young's modulus of not less than 8,000 kilograms per square millimetre are claimed. With 50% cold work, hardnesses of at least 150 are claimed. Thus, in summary, it is evident that microalloyed platinum alloys are possible, although it is not clear whether they're being commercially produced, and that the rare earths and calcium are preferred microalloying additions, paralleling that of the work on gold. So we can just come to my last slide. I think we can conclude that the metallurgical basis for strengthening and hardening 24-karat gold of at least 990 fineness has been reviewed. This shows that as well as titanium additions, calcium and the rare earths to be the preferred microalloying additions, but other possibilities have been noted. Commercial alloys are available and jewellery is being made in these alloys. The advantages and pitfalls of such alloys for jewellery production have been summarised. The extension of this approach to hardening of 22-karat golds has also been reviewed, where the use of titanium, cobalt and antimony are the preferred additions, mostly as microalloying additions. Hardening of silver and platinum by microalloying has also been reviewed, and their metallurgy parallels that of gold. The silver materials are known to be commercially available in the USA. And lastly, I'd just like to thank many friends and colleagues in the industry for their support in providing information and allowing their data and figures to be used. And I also like to thank the staff of JTF and Legor for inviting me yet again to present once again and for their kind hospitality. Thank you.
Ringraziamo il dottor Corti.
Thank you very much, Dr. Corti. And now the time has come to introduce the next speaker, who's new for the audience of JTF, Fabrice Barbeau from Hilderbrand, who's going to talk about induction heating as applied to brazing and its applications. Dr. Barbeau is an expert in material chemistry with over 20 years' experience in the transformation of metals, with a specialization in brazing and soldering with laser. He has worked in different industries, from the automobile industry to the production of a special copper alloys up until top-level watchmaking industry. Now he's a chief technical hospital at Hafner and Hilderbrand. The presentation by Dr. Barbeau provides us with a presentation of induction heating and its application for brazing and the potential development in the watchmaking and jewelry industries. Physical principles will be explained, as well as the advantages to be drawn from this technology, highlighting the key factors for success. And finally, certain applications will be shared. So over to you, Dr. Barbeau.
Last year, during my previous visit to the fair, I was surprised to see that induction heating is very poorly representative. Also, it has considerable industrial importance. My presentation is divided in 5 parts. I first introduce myself. After, I show you the requirement of final assembly for luxury parts. And after, I present you the induction effect, and finally merge the assembly for luxury parts and induction effect. At the end, you have to remember the highlights. So myself, first, I just apologize for my lovely French accent. Shortly, I have about 30 years of experience in welding and brazing, including 20 years in luxury sector. Now, I introduce you the well-known lobster clasp. On your left, the entry level with mechanical wing enclosure. The main problem is the gold alloys are very soft. So over time, the ring open spontaneously. So it's not compliant for luxury. On the other hand, on the right, you can see a brazed lobster clasp with a continuous metal link. So it's as Roma, only the metallic link is eternal for wedding ring. Another way, two ways to create a completely metallic link is brazing and welding. For welding, only the laser is compliant with luxury requirement due to small pieces and very high pressures. For laser welding, laser ray melt locally the 2 different parts and create a definitive link. For brazing, the key point is to insert a low melting alloy, not too low, and during heating, the low melting alloy create a definitive link for assembly the 2 components. Sorry. I just insist on a wording. What we have to say is, what is it, solder paste or brazing paste? According to the standard, the term soldering, also called soft brazing, must be used for assembling with filler metal at a temperature under 450 degrees. For instance, when using tin-based filler metal for assembling electronic components, It is called soldering, and so the filler metal is called solder paste. The term brazing, also called hard brazing, must be used in the assembly is carried out at a temperature upper 450 degrees. It is always the case for luxury goods. Subsequently, only the term brazing past will be used. Welding is very interesting for very high mechanical strengths, and it is possible to use a filler metal exactly with the same composition as the base metal. For brazing, the key point is the aesthetic of the joint. So, welding with a very, very local heating, and so it affected zone. Welding is very interesting for repairing. Brazing with the very high quality and the possibility to braze the finished part is perfect for first production. Brazing overall process. There is some subsequent operation, machining, deburring, washing, and you have to pre-assemble the components, and you have to dose the filler metal. The heating process of brazing can be performed by a furnace, torch, or induction. And the next step are finishing, grinding, something like that. The brazing filler metal requirements. The key points for filler metal is melting point, which should be as high as possible, but not too close to the component's melting point. Suitable to the application means the right metal, first the right metal fineness for 18 karat gold, the right color or the closest color is possible, and the mechanical requirement for luxury goods. What is brazing paste? A brazing paste is a mix of a flux, a binder, and a powder metal. The flux have a first shielding effect on the components, and when it completely melts, it creates a desoxidation in order to protect the filler metal. The binder allows the powder to be packaged and dispensed. So brazing paste is all-in-one, ready-to-use product. Some key points about the brazing paste. First, I insist on the color. On the right, you can see the syllab diagram that presents the three basis colors in a board. As you can see, 4N and 5N, pink and red golds, are on the left, and traditional alloy, using in bulk way, is quite far from the real color. A key point with brazing paste that you can create a very fine alloying that very close to the regular color of 4N and 5N. For the Hilderbrand binder, contain no water, so it's not drying. The brazing paste is compatible with main heating process, such as induction or torch. And brazing paste is very easy and to dispense. I don't know how to start the video, so I just made a short overview of the video. Yes. So first, the binder evaporates. Second time, the flux is melt, and third time, it's not precisely, but the metal flow, as you can see. So event evaporation, flux melting, and metal melting. Induction heating. So induction heating, it's Michael Faraday is credited of discover the induction effect, and the mathematical James Clerk Maxwell put the effect in equation. We have just to remember that the Maxwell's equation links magnetic field with electric field and electromagnetic force, and it can lead to the electromotive force. With the equation, you can calculate the power of induction effect and the thermal efficiency. But in all days life, what it means? Many people use induction for heating their morning coffee using Italian coffee maker. The well-known Massimo Bottura Italian chef used induction hob. And the induction effect is widely used, as they show in induction hob for cooking, but the capacitive touchscreens, sorry. The capacitive touchscreen use induction effect, electrical motor, power generator, or airport detector. Industry in a metallurgic plant, induction is used for quenching, forging, and melting. What is really the induction effect? When you move a magnet near a coil, it creates a current. And the reciprocity, when a current flows in a coil, it creates a magnetic field. If you have not a continuous current, but you're replacing by an alternative current, it creates an electric and magnetic fields. And reciprocity, electric and magnetic fields in metallic materials create alternative current and basis on eddy current. And heating of induction effect is done by the Joule effect on the eddy current. So, as it's shown on the induction hob, the induction coil in the induction hob creates a magnetic field. The cookware is based in iron materials, insensitive to induction field, so an eddy current is creating, and the heating effect appears. So thanks to this eddy current, it is possible to heat without contact a conductive piece. Electric and magnetic fields act at a distance. So first is the well-known effect is the magnetic levitation. It allows to melt an alloy without crucible. In the second, the greater the applied current, the greater the eddy current, resulting in a great temperature inside the product. The induction power only runs on conductive materials. So, for instance, the egg cooking is only on the metallic part. Due to the electric and magnetic fields do not penetrate in conductive materials, there is a skin effect, and the induction heating power is linked to the frequency. In real, the induction tools are quite easy to do. You can do it by your own, and the starting point is a single wire loop. And and in the technical terms, multiply the effect by n. As I explained, induction effect acts as a distance, but it decreases very quickly with the distance. So the coil have to be as close as possible to the heating zone. And the induction effect depends on the materials. As it shows, stainless steel, titanium, graphite are very good candidates for induction heating. The resistivity, the poor resistivity of gold and silver is a problem, but there is a very high density material, so it is possible to heat with a good, it is possible to heat gold and silver metal. In this table, I show you the PTFE, Teflon, quartz and alumina. They are widely used in holding and enclosure system for induction. Due to their very high electrical resistivity, they are not affected by the induction effect. So, induction is a very local heating. It is quite easy to make automatization, and it's a physical process control. Now, so the first tool for induction can be by do-it-yourself. It's easy with the hand. This is, as I explained, a very reproductive physical process, and it's a safe process. No flame, no gas. A brazing paste is all-in-one ready-to-use product and is very easy to dispense and dose. So the basis of the induction setup is a power generator, an induction coil, and a ceramic jig, and if you need, you can put shielding gas. And with equipment, so there is an AC power supply, alternative current supply, transformer, that's the box, the gray box. It is mainly, we add a pyrometer in order to follow the temperature, and you can see the workpiece in about 800 degrees. There is some key point to refer to the manufacturer about the AC alternative current frequency and the induction coil length. The induction brazing assembly start mainly with a holding tool or pre-assembled with induction laser dot or resistivity pre-assembling. After, you have to dispense the brazing paste, put in the holding tool, heating and cooling. There is two ways of induction. Direct induction heating, you put the components closest to the induction coil or something like that, or indirect heating, and mainly you use graphite susceptor. And in production line, the basic setup, the setup starts from laboratory setup. You can full manage the equipment with a semi-automatic process, mainly based on rotary strand, and sometimes a full automatic process with belt conveyor. Some example of high-end luxury. Many bracelets clasps are brazed using induction heating to have only a local heating. The well-known lobster clasps sometimes there is a spring inside. There is very sensitive. The spring is very sensitive to the temperature. So to avoid softening, induction heating is very interesting. The brushless ring is a good candidate for induction heating because it avoids to heat a second time the bracelet, and with the risk with the apparition of orange peel or something like that. In high-end eyewear with full metallic frame, there is some pieces that are widely that is brazed using induction heating. In a watch clasp, the pin can be welded with induction heating to avoid to heat treat the clasp, and some high-end watchmaker insert some gold part in full stainless steel bracelet. The highlight. As I showed, the induction heating with brazing paste is very adapted to the luxury goods. It's give a full, a very high quality process, and have all the requirement of high-end and luxury goods. But it's a cost-saving process. It reduces the number of operations. For instance, you don't have to add a subsequent workstation in order to fix the filler metal. You don't need to put some flux because in the brazing paste all the components are in. It's process would be safe without flame, and it expand assembly possibility. You can braze very close to precious stone and clasp string, for example, and it's compliant with metallurgical properties of material, such as materials that's sensitive to orange peel or cracking. Thank you very much.
Ringrazio il dottor Barbeau.
I'd like to thank Dr. Barbeau. So, as we have to have lunch at 1, we have decided to postpone Mrs. Luana's presentation to this afternoon. So now the time has come for Fulvio Sinisi, who will speak about silver tarnishing protection, state-of-the-art, and other studies. So after graduating in Padua in 2016, he started to work at Legor, where he is now R&D manager. And he deals with the formulations of new techniques, improvement of already existing projects, and he also manages the technical support for the plating department. So we will have a presentation on silver, who is subject to oxidation and tarnishing. And the presentation assesses the situation from the physical and chemical viewpoint and possible techniques, anti-tarnish techniques. And we will
see a case study showing the different ability of various methods in order to improve tarnish resistance. And the objective is that of offering an overview on the state-of-the-art of the current solutions and the importance of advanced tests in order to improve the protection of silver.
Grazie mille e buongiorno a tutti.
Well, hello, good morning. As Andrea already said, we will focus on silver tarnishing, starting from the description of the phenomenon, the removal of the tarnish, anti-tarnish treatments, and evaluation of the efficacy of these treatments. And then I will show you a case study during which various solutions, various technologies have been tested related to silver tarnishing. And we will see the various tests and the different performance of these different tests. Well, silver has long been used for the production of precious jewels, and this is due above all to the fact that silver is the metal with the highest brightness, and so it can have brightness. And it is a metal which is easy to use. It has a long duration resistance, and although being a precious metal has a relatively lower cost if compared to gold or platinum, and the motivation is also related to its abundance in nature and lower mining difficulty, above all compared to gold. So, although being a precious metal, silver is subject to some reactions which can change its aesthetic characteristics. This is called tarnish, and it is a spontaneous reaction between a metal and a non-metal, oxygen or sulfur. In the case of silver, the tarnish reaction is described by this chemical equation where silver reacts to sulfur. Sulfuric acid is identified without atmosphere, thus giving rise to silver sulfur, which is the tarnishing. Well, we should specify that this phenomenon is a very complex one because it involves a whole series of reactions which take place simultaneously. And the identification of sulfur composites is not enough because there are various composites which intervene in this reaction. Tarnish is a surface reaction. It involves only the first layers of a silver surface, and according to the thickness, there are various colors from yellow to black, which is the real color of sulfur. Well, there are various reasons for that. Certainly, the concentration of tarnish compounds, which increases the level of tarnishing, thus accelerating the kinetics of the process. And also temperature plays a very important role because temperature itself is a variable which contributes to process kinetics, and then it increases the pressure of sulfur vapor and humidity. Although not present in the reaction, has in fact a very important impact on the tarnish of silver because the absorption of water vapor is the perfect means to accelerate this type of reaction. And then certainly the purity of silver, because often silver objects are alloyed metals which have a greater reaction to sulfur compounds. So an impure silver object is more subject to tarnishing as compared to pure silver or galvanized silver. Well, the thickness is itself a barrier. And as a consequence, the greater the thickness of sulfur, the slower the reaction. And indeed, the tarnish reaction is a self-limiting phenomenon which involves a low layer of the surface, and it is possible as a consequence to remove the tarnish layer, which will not attack the whole bulk of silver as can happen in iron. And as a consequence, once you have removed the layer, the surface of silver will show its proper chemical and physical characteristics. But of course, as the silver layer is exposed to atmosphere, it will be subjected to tarnishing. Well, there are various techniques. You can use abrasive systems, and the notion is that of mechanically removing the tarnish layer. Well, a certain portion of silver will also be removed. Well, of course, it's a very small quantity, but we have to underline that. There are also other systems, chemical and electrochemical systems. Here, for example, we have a homemade system based on electrochemistry where aluminium is involved. And what is suggested in many sites and meetings is that of plunging the silver objects in contact with an aluminium paper, thus exploiting the reaction, the chemical reaction. Well, it's a process which has not a high level of reproducibility because there are a series of actions which can make this process non-effective or even allowing for the new deposition of this problem. And then there are chloride, peroxide solutions. These are very aggressive products. They can attack the underlying surface. Well, you can also use common detergents you can find in all shops, and these are based on the presence of some mineral salts which have a modest abrasive function, and sulfur is bound by some chelating agents, and aggressive molecules are dispersed. And then there are industrial products which use reducing agents which reduce metals. There are chelating agents which bind sulfur, and then corrosion inhibitors which avoid the re-aggression of silver for a long period of time. Now, as a consequence, well, we have said that tarnish is a spontaneous reaction of silver. So even if you remove it, the surface will still be subject to tarnishing. So what you have to do is to slow down or avoid this type of reaction. It's impossible to stop this process. And so our approach is that of preserving the object with a certain care, avoiding the exposure of these objects to pollution or atmosphere, and then use some anti-tarnish solutions. Well, there are various products, various technologies, all based on the same principle, that is that of creating a barrier in order to avoid the contact between the surface of silver and tarnish agents. So we used silver objects. In some cases, polymers were used or passivating solutions were used. And finally, recent studies have focused on the use of new technologies for the deposition of nano substances. Well, rhodium, for example, has a high resistance to tarnish with high chemical inertia, and then it is a precious metal, and so it increases the final value of the object. The problem is that the thickness applied is lower than 0.2 micron, so the resistance is guaranteed, but only for a short period of time, because the thickness will tend to be removed, and the surface of silver will be again subjected to tarnishing. And then rhodium is a white metal deposit, but it is less so as compared to silver. So if we had to express the white color with these CLA activities, well, rhodium has an L equal to 90. So we have a certain level of resistance, and then the final cost increases, and it is subject to the oscillations of rhodium costs. Well, the application of organic polymers make it possible to have a good defense, because there is a high thickness beyond 5 micron. Systems of applications, we have various types of applications, and the costs are low. The big problem of this type of material is that it is a plastic material, and it gives the objects a plastic aesthetics, and as a consequence, and then apart from being transparent coatings, the thickness is such that it changes the reflectance of light, and so the final effect is that of a color which is much darker. These are more complex processes as compared to rhodium. There are some difficulties in the application, and you have to have higher qualified staff. Now, the most used systems are so-called passivating solutions. In the past, CR6 solutions were used with a high resistance to tarnishing, but they are based on CR6, which is highly toxic. And then other solutions have been used. Benzotriazole, for example, is more prone to copper than to silver, and so it is often used for copper alloys in the electronic sector. Organosilicates are effective, but the problem is that they are difficult to manage because they are dissolved in solutions which are difficult to handle, and they are not so stable as compared to other solutions which are much more used for passivations. And these are TiO-based solutions. These are compounds based on carbon atoms. So there is a connection. And these compounds are called self-assembled monolayers. These are molecules which interact with a metal surface and can be absorbed and can organize independently as to create a homogeneous layer. In terms of silver, these are very useful because they can bind to the silver surface and they create a connection, a bond, and they make the surface hydrophobe, thus slowing down the absorption of humidity and the interaction of the surface with the sulfur compounds. Thickness is small, so you have invisible layers which maintain the brightness unchanged. These are very simple to use and low cost, and they are low cost methods, and they are today the ideal solution to preserve silver objects. The great disadvantage is the small thickness, which means that they have little resistance to wear, and so they are not the ideal solution for many situations. Recently, vacuum technologies have been developed with the objective of depositing a barrier, thus avoiding the interaction between silver, humidity, and tarnishing agents. The methods of applications are two. They are called TIO or PVD or ALD, physical vapor deposition, which grows a material on a layer starting from the evaporation and successive condensation in a vacuum system, starting from a target which is eroded and evaporated. We have a growth of a few microns per hour, and the temperatures can be as high as 1,000 degrees per centimeter. And then for anti-tarnish coatings, we can use ALD, which means atomic layer deposition. It is a technique which grows single thin layers by means of impulses made with gases and inert gases. So a series of cycles which produce homogeneous compact layers with the very high growth rate. And in this way, I can control growth by means of chemical reactions, and I have a high level of control of the growth, and the pressures and temperatures involved are less high than DVD, and also pressure is lower than DVD. So this technology makes it possible to create high resistance barriers with the low thickness, 15, 40 nanometers, and such a small thickness can be very effective. And there are studies which have demonstrated that the same deposit has the same resistance with a similar deposit made by PVD and deposits above 5 micron made with normal polymer-based resins. And this makes it possible to control the thickness and control also the compactness of the layer. So in the case of higher thickness, there can be an impact on the aesthetic characteristics of silver, so you have to use thickness lower than this value. These are highly specialized techniques based on vacuum techniques, and there are high costs in terms of technologies, and also the staff must be highly qualified, and all these costs may have an impact on the final cost of a silver object. Now, in order to assess the resistance to tarnish of all these systems, tests have been developed. The most frequent tests are those where the silver surface is exposed to sulfur. It can be vapor, or immersion in solutions, sulfur sodium or potassium sulfur. Now, it would be appropriate also to check the resistance of these objects, exposing these objects to other compounds, whether it's chloride or whether there is humidity or ultraviolet reactions. It would be interesting to carry out a real-life test to all the possible complex situations. Now, all these tests are not specific for silver. They are used in other sectors. So today it is very difficult to define objective criteria to assess the efficacy of these anti-tarnish treatments. The assessment is normally based on tests which include the exposure to sulfur. And there are some difficulties in interpreting these data because the same treatment often has results which are very different from other tests. So today the approach used is that of having a series of tests, different tests, hoping that there is a certain correlation between similar tests so as to identify the efficacy of the anti-tarnish operation. Now, I'd like to show you the results of this study that we carried out at Legor with the objective of comparing 8 passivating solutions taken from the market, all based on SAM systems. Different sterling silver layers were tested, and we did TAA tests and the immersions in 5% sodium sulfur solutions for 20 minutes. Now, results were assessed in a visual way, but a more objective evaluation was made with the use of a spectrophotometer. These are the results after 48 hours. And what emerges here is that there is certainly an anti-tarnish effect in passivating solutions tested, because we see the difference in color between the non-tested product and all the other products. But it is impossible to differentiate the efficacy of the various treatments, because all the compounds have had good results, and it's difficult to say what is the best sample. And then this test was made, and in this case, after the first 5 minutes, we could see differences between the various products. And at the end of the test, lasting 20 minutes, results were confirmed. There were no significant changes. And if you look at the L value, which is the brightness and the white color of the silver alloy, well, you can see that there is a difference between the various treatments, and after the first 5 minutes, results are evident. 3 samples overcome the test with a brightness greater than 95, and all the other samples did not did not achieve the same results. Now, in conclusion, what are the next challenges? Well, First of all, we will have to establish a series of tests specific for silver tarnishing. We will have to have the most accurate possible simulation of the real exposure conditions, and then we should have a correlation between the test results and the life of the object, because very often customers ask us how long will the result remain? Well, for us it is impossible to give an answer because the tests which are made do not give these types of results. They are comparative tests, but I cannot say how long an object would last. So having tests which can give this type of answer would be very interesting, because it would promote the development of new anti-tarnish treatments, invisible treatments with a high resistance to tarnish and also lasting over time. Thank you.
Ringraziamo dottor Sinisi, concludiamo quindi la sessione del mattino.
Thank you very much, Mr. Sinisi. We're going to meet again at 1:45. Light lunch is served just outside this hall. Thank you very much, and see you soon at 1:45. Thank you.